And chapter 2 consists of frequency tables and histograms. And the textbook make a real meal of this. They make it a lot harder than it really is. So if you're reading the textbook, you probably will be more confused than helped. So it might be a good idea just to follow what I do and you'll be fine. Bar graphs are good and stem and leaf are good. So those are the three things that we're going to be dealing with and covering today. Essentially what we're looking at is how do you take information, right, data, and summarize it in a way that makes it easier to see what's going on. So by the kind of summaries I'm talking right now are putting that information into tables that we can see, you know, rather than just have the data all written out, and pictures. And pictures can be things like bar graphs and stem and leaf and histograms, essentially. But there's a little bit of pie charts and some, what was the other one? Dot diagrams, scatter plots. Are we cool? Right. Now, this might seem a little bit back to front and upside down, but since they make such a meal of 2.1, I'm going to keep that to be the last section that we do today. And that way I can figure out how much time we need to devote to it. And I won't feel under any pressure. So we're going to look at section 2.2 first, which deals with bar graphs. Well, essentially, let's take a very simple situation. Suppose that you had a table and you had favorite color and the frequency. So you asked a number of people, what's your favorite color? And they could only pick one. And you had some people said red, and some said blue, and some said green. And lastly, some said, say, yellow. So this is a little baby version of what a big version. So there was 12 people who liked that, 5 who liked that, 3 who liked that. What's that add up to? It's 20, 10 they liked that. So here's a table. We've already summarized the information. Do you see what I've done is collect all this categorical data, and we've just looked at how many people in our little sample of 30 people, which is what that's telling us, said that that was their favorite color. So that's basically a frequency table. Now, when you do these types of diagrams, the vertical axis is the frequency and the horizontal axis is whatever the variable happened to be. In this case, the variable is color. And you do red, leave a space, blue, leave a space, green, leave a space, oops, a little bit more room here. This is it, yellow. And since the biggest number I've got is 12, I could probably get away with 1 square represents 1. And you simply take red, and there's 12 people who liked red, and you judge, I think that's roughly where 12 is. You draw that. And you go to blue, and there's only 5 of them, and you go like that. You do green, there's only, what, 3 of them, that's probably about here. And you do yellow, and there's quite a lot of people for yellow, so it's up like that. Pretty primitive, right? There's not an awful lot in that process. But when I look at this chart, and I look at the table, I think I can get pretty much the same kind of information. This kind of data, right? This is nominal data, right? There's only, you can't really put it in order. I don't think you could say that red is more or better in some respect than blue. You could jumble these up and it wouldn't have any effect, right? There is no order we're talking about. And we indicate that by the spaces. So in this case, we've got color, we've got frequency, and the height of the rectangle. This information is the same as this one. This is just a visual representation of it. So if I give you this information, shouldn't you be able to create a bar graph? And if I gave you this bar graph, couldn't you construct a table like this? Now, what kind of information? You don't get an awful lot of this, but there's not an awful lot of information you can get out of this type of data. Can't you look at it and say red's the most popular color and green is the least popular color? And I guess you could probably rearrange the colors in order from most popular to least popular. And that's about the end of it. You can't do pretty much anything else to this data. It's kind of quite minimal what we can do with it. So don't expect to do a lot. You know, draw it and maybe answer a question or two and call it good. There are certain things you definitely can't do with this data. Do you know there's no reasonable way for me to add these up and say that the average color was kind of reddy yellow with a touch of blue and green in it, right? It doesn't make sense to do that, right? So you can't average this type of data. You can't really do, as I say, much more except create a frequency table and a bar graph. So what I'm going to do now, hopefully this works out the way I think it should. When can I find things on it? What is it there? Right. Oops, almost overshot it. Okay. Shrink this back just a touch. Right, so what we've got here is the introduction to what bar graphs are. So some of the features. Bar graphs can be vertical or horizontal. So although you can't see it, see that graph I got? See if I picked the paper up and did a little 90-degree, can you imagine the rectangles going horizontally instead of vertically? Here is some, oops, it jumps very quickly. Here are some examples of bar charts. In this particular one, have you noticed that the two rectangles are next to each other? And along the bottom, it's a year. So in 1980, you've got this light blue, which is men, and this purple one next to it, which is women. So for instance, the way you would read this piece of information is in 1980, the average age for men was 70 and the average life expectancy for women was 77.4. And then if you look at the year 1990, year 2000 and 2010, you can get a little bit of a pattern going on here. This data is years, and I know that years look like numbers because they are, but they're not really numbers in the usual sense of the thing. They're just ordinal data. They're just labels that represent it, but they have an order in them, right? 1980 before 90. You could probably say it was interval as well, I guess. What I can ask from this kind of data is quite interesting. If you just look at the men on their own over the time period that we're talking about, would you agree that as we travel from 1980 to 2010, the life expectancy of males has gone up? Every year or every 10 years, it looks like it gets like a year better. And the same thing is true about the women, right? It's improving as well. The second feature that I notice is that no matter which year you pick, don't women live longer than men? You agree? Women live longer than men. So that reminds me of a really bad Scottish joke. So let's get that out of the way. Why do Scottish husbands die before their wives? You meant to say, I don't know. So here, we'll try it again. Why do Scottish husbands die before their wives?
I don't know. Why?
Because they want to.
Oh my God, that was funny.
Was that bad? Oh, you liked that one? I never know you like.
That was
Okay.
funny.
That was funny. Okay. So this might be proof that that is true. No, actually, it's more to do with lifestyles and, you know, the jobs that men do compared to the jobs that women do and so on, typically. Now, when you see this bar chart, the data next to it is actually the same bar chart. There's one little feature. Do you see that little broken zigzag? See the little mouse, I don't know, the little mouse, do you see that little zigzag just above the 0? Can you see that this time the vertical scale is starting at 65, whereas over here it starts at 0? When you look at the information in this format, doesn't the difference between males and females become more obvious? You can see that this rectangle is clearly a lot smaller than this one. Would you agree that you can also see the rectangles getting higher? So that idea of every year we live a bit longer than we would have on average, you know, the decade before. That's also there. So when you are adjusting the vertical scale like this, one of the reasons you may be choosing to do it is just to show whatever the pattern or trend is, to make it a little bit clearer. The disadvantage in doing this is that you can make differences seem very big. When you look at the pure data, right, starting at 0 going upwards, do you see that there are differences here? But they're not that big, right? I mean, 7 years is important, but it doesn't look huge compared to each other. When you look at this, doesn't this fella here, the women, look like it's twice as tall as the males? Do you see that gives you a false impression of relationship, how big the difference truly is? So you have to be really careful if you're doing a bar chart and you're going to do this little breaking of the vertical scale, that you don't inadvertently make people think that it's more important than it is. Here's another one of these charts. I mean, there's lots of reading. Here is a pie chart that nobody I know ever likes, but there's one there anyway, so we'll show you. And here we got another kind of chart, which is called the time series. So how does that one work? Well, imagine that you collected data over a 20-week period. And underneath you had the distance in miles walked or jogged in 30 minutes. And this is, you know, on week 2, he did she did 1.4 miles, and in week 17 it was 2.5, and week 20 it was 2.7. If you take this data that's in the form of a table, it's very difficult to see any pattern. It's called a time series, this kind of graph, because the top variable is some measurement of time. In this case, it's weeks. But you can imagine it might have been day 1, day 2, day 3, you know, or something like that as well. Now, if you take this data and along the x-axis, you label it week 1, 2, 3, 4, 5, 6 up to 20. And then in the vertical axis, you go from, well, technically 0 to whatever the biggest number is, probably 3 is plenty. Can you see that what each one of these dots represents one of these pieces of data? So let's at random. In week 5, that person covered 1.9 miles. If you go to week 5 and you go upwards, that red dot is at a height of 1.9. And when you see this, do you see that there is a pattern going on? It's not a clear pattern, like it's perfect. But would you agree that as the weeks go by, this person is walking and jogging more most of the time, right? There's a couple of bad weeks where he went down, but it's pretty good, right? And can you imagine you were on a 20-week diet and this represented how many pounds you lost each week, right? This would be a really cool diet. Actually, diets tend to go the other way. Because at the beginning you don't lose much, but every week aren't you losing more and more than you did the previous week? If I did a diet one, I would expect a kind of zigzag going down the way. It's much easier to lose in the first 2 weeks of your diet than it is in week 19 or 20. So we're just looking at all the kinds of visual kinds of graphs they are, right? So we've looked at bar graphs, parental ones, very similar. The circle ones I really skip by because I'm not even going to ask you questions on those guys. Time series, we just saw one there. And whenever you do a graph, there are certain things all of them should have. They should have a title. This is a graph of how many days I walked in the last 20 weeks. Or this is a graph that represents the favorite color of children at kindergarten, or whatever it might have been. You should also have the axes labeled, right? So the horizontal axis should be the variable. So that would be things like the color, your favorite TC channel, whatever that might be, TV program. In a time series, the horizontal would be the time units, right? Week 1, week 2, week 3. Or 1 minute, 2 minute, 3 minute, if it was an experiment and you were recording temperatures at, 1 minute intervals. That would be what that would be. And your vertical scale would be frequencies. How often did that thing happen, or what happened at that time? Now let's look at interpretation. Consider the graph A, the reasons people like texting on cell phones, based on a GfK Roper survey of 1,000 adults. In the first one, it's a bar graph, right? Isn't it a bar graph on its side? If you could take that and turn it around, wouldn't it look vertical on you, right? So bar graphs can go that way. I've seen them in magazines this way. And here, they look like that. Now, what's the difference between these two and how we got here? Well, the height of this one is 25, this is 37, this is 56, and this is 79. So can you imagine there's a little invisible scale up here going 0, 10, 20, 30, 40, all the way up to 80, 90, 100. So if you wanted to represent 79% in this one, don't you just make the length of it 79 units to represent 79%? What's happening here is not that. Why does 79 look like this and 25 looks like that? What else have they done to the rectangle to try and change the way you view the information?
They've taken and made it wider.
Right, and big gets wider and little gets skinnier. So in a way, aren't they trying to emphasize that 79% is bigger than 25%? You see what she's saying, wider from there to there, I guess I'm calling that wide, right? You see how that's much wider than this? Now, visually, when you look at this and you look at this, doesn't this one kind of stand out more in your brain, or at least in my brain it does? Can you see that 79 looks much more important than the 25? Whereas over here, it's kind of skinny, and although it's the same information, it's a little bit less easy to see it. So you have different kinds of situations here. Here they have, they're just going through various examples. We could do them forever. Right, let me just leave that guy for a minute. So there wasn't a lot in bar graphs, were there? There was bar graphs, there's time series, and a couple of examples of how you can change the way things look to make them a little bit more interesting, or a little bit more, what's the word I'm looking for, visible. Now, you can't expect too much in the way of questions from this section, I'm assuming. So let me see if we can get this. This is bar graphs, and we'll do a quick view. Are you lot looking at section 2.2 bar graphs? Can you see it? Okay, so I don't need to go out and in. Notice how few the questions are, right? So when you look at your homework, you're going to see tons of different sections to go, and it might freak you out. But if a section's only got 5 questions in it, it's not really a lot of work, right? So don't think you're going to get overwhelmed. Wait till you've actually seen what the questions are and how much you should do. So let's look at question 1. It is costly in both time and money to go to college. Does it pay off? Well, according to the Bureau of the Census, the answer is yes. The average income in thousands of dollars of a household headed by a person with a particular stated education level is as follows. 24.3 if 9th grade is our highest, then it's 4.1 for high school graduation. So if you graduated for high school, you would make about 41.4 thousand. That would be your household income. It's up to 59.7 for those who have an associate's degree, right, a 2-year college. 82,000 82.6 thousand for a bachelor's degree. 100,000 for a master's degree. Cool, and worth a lot of money. And 121.9 for a doctoral degree. Of course, if you're a doctor, you could probably quadruple that money, right? So a doctoral degree could be, you know, a doctorate in physics or something as well. Now, when you look at this, can you see that there are 4 histograms? Now, look really carefully. It's almost like they're not. Can you see that the gap between them is tiny? But it is there. Agreed? Now, when you look at the horizontal one, they should have put a label there. Shouldn't they have said something along the lines of highest education the householder reached? You know, something like that. But can you see if you quit at 9th grade, or you waited till you graduated from high school, or your associates, or your bachelor's, your master's, your doctorate, you see that has a very nice flow to it, doesn't it? Now, they gave us the raw data up here. And can you see why this one here is the right answer? I didn't really need to draw that one, but I guess if I did it as some scratch paper and then I came back, I would be able to tell which of these 4 guys it would be, right? Now, that's a cool question, but it's not a hard question, right? Once you actually read it, it's got a little tag on it, you can see that's the right one. I think this question would have been much more interesting as, see if you took the wrong answers, which are these 3 pictures, but you did something to each which just got you to think. Isn't this the most natural order that you would put along the horizontal axis, right? 9th grade up to doctorate. Is this ordinal or nominal data?
Professor, just to interrupt real quick, I think
Yes?
we're saying WebAssign.
Oh, darn it, in Spice. You're meant to tell me these things. I thought I got an okay on it and I was wrong. Okay, that's what you should be seeing now, right? So when I say I have to go in and back out, that's what I have to do to make sure you see it. So can you pretend, we're not going through the whole question again, can you see why this guy works, right? But the question I was asking, is this data, these things along the bottom, is this ordinal data or nominal data? So this is a question back to chapter 1.
Nominal?
Okay. If it was ordinal, what would the difference be?
I was going to say ordinal because there's already a natural order to the degrees.
I would agree with you. That's why I kind of rephrased my question, yes. Would you agree that this particular set of data has a natural order to it? And when the data is like this and it has a natural order, it's ordinal. Think of it's got an order, ordinal, right? There's a kind of clue in the phrase, right? Nominal is like the worst kind of data in the world. That's like red, blue, green, yellow, right? There is no order, no normal, sensible order that you could do with that. And what I was thinking is it would have been interesting if they jumbled these up, and so that you could have the same data, but the only one that would actually be the best one would have been this one. Because, well, I guess you could have doctorate down to 9th grade. That's a kind of natural order. That would be from the people who make the most money down to the people who make the least. A piece of sharing data, because I like to share data, social science data in this case. Do you know that the best way for you to not be poor. If you're a woman, this is different from a man, strangely enough. If you're a woman and you want to have a good lifestyle, right, make money and have a good household, finish high school, do not have a baby out of wedlock, because that screws up your education. The guy will bugger off, right? But you won't. You have to look after the little tyke because he's yours. Those are the two main drawbacks to people actually advancing educationally, if you're a woman. For men, it's finish high school. If you look at the data, unmarried, I don't know how you phrase that, but you know, if you've got a baby and you're not married and you're not in a stable relationships are fine. I don't care if you call it married or not married. That's not what we're talking about. The married's not the important part. The stable relationship is. But if you have to look after a baby on your own or babies on your own, isn't that going to screw up a lot of your opportunities? It just is.
Yes.
What's the advantage to the guy? They bugger off. Pardon the phrase, don't they? So in fact, they might not even pay child support, right? In which case, so don't know where that information came from, but it's a very good piece of scientific data. Unfortunately, there's a lot of people who, life gets in the way of good decisions sometimes. Okay. So that one there is pick the right picture. Here is the data, pick the right picture. Oh God, let's do it, because I thought I had missed all the circles. Commercial dredging operations in ancient rivers occasionally uncover archaeological artifacts of some importance. And what that just means is that you drag in the river and you bring up a sword or something. On such artifacts in the Bronze Age, spearheads recovered in an ancient river in Ireland. A study gave the following information regarding discoveries. Right, these are the 5 rivers, and these are number of spearheads they got just by cleaning up the river, right, dredging the river. And here are the pictures. Now, I don't think you should have problems figuring out which one goes with which. You just have to notice that Shannon went first with 33. So just because it's in this table, they didn't actually make it in this order. They did it in this one, which is fine. But the one that's really the one that's interesting to me is, not so much interesting, I just want it out of the way. Do you see that the pie chart of the same information, how difficult it is to tell that this guy here is the real one? Because if you want to know this is the real one, first things first, do you know you have to take this guy here and find out what percentage he is of the total? So what's that add up? 29, 39, 44, 74, 77, 87. There's 91 things there. So 14 out of 91 gets you that one, 19.8%. I think it's pretty convincing why pie charts are pretty much ignored for most situations. They're just not very cool. Do you recognize this one as a time series? Right. Time period 1 to 15, elevation. Can you imagine drawing it? Which one of these fellows it would be? Right. If I didn't do any drawing at all, why am I picking this 4th one? Just looking at the numbers, why is this one the guy that's going to win?
Well, because the numbers simply, I'm having a hard time seeing that,
Right.
decrease. And there's no change, fluctuation up and down.
Yeah, they basically just get bigger. So that's an uphill one, right? So I know it's that one, which it is, but you can tell that. There's a fun picture. I'll let you suffer through that one. It's the last question, so there's no biggie. So did you see that probably that entire section might take you 15 minutes? Right, so I know there are going to be a lot of sections in that that you have to kind of deal with, and if I actually go back again to page, you've got 2, 1, 2, 2, 2, 3 in a review to do. And you've also got, this thing kicks over, 3, 1, 3, 2, 3, 3 and a review to do. Do you see? So chapter 2, chapter 3, there's a lot of sections there. But you've already seen one of them that didn't take any, I think, didn't take any great length of time. So the next fella that we're going to look at, okay, are you looking at a PDF of a thing called a stem and leaf? Can you see that?
No, it's still on
No.
the sign class view.
Right, so let me go that out and in again. Okay, can you look at stem and leaf displays now? Right.
Yeah.
So after I've found that, I'm going to stop and show you my my version first about how you do stem and leaves. It's a visual diagram based on how to take your data and draw a relatively quick picture of it. And these pictures are called stem and leaf. So let's suppose I've got a whole load of data, and I'll put the data in order just to make my life easier, but it might not always be in order. Right, so there's a whole load of data. Maybe it's the ages of people in a statistics class. And we would like to take this data and visualize it, right? Draw a picture of it to make it a little bit easier to see. So what you do in a stem and leaf is you create a thing called the stem. And in this data, we start on the teens and we finish on the 50s. So I'm going to go 1, 2, 3, 4, 5. Now, changing color, just because I can. 15, you just put a 5 there. 16, you put a 6 there. There are 2 17s, you put 2 7s. Next number is 21, 25. The next number is 31. Oops. 31, 37, 37, 37, 39, 41, 43, 45, 46, 46, 46, and finally 51. Right. Apart from that little mess there, can you imagine that that's a very quick way of taking a whole load of data, especially if it's in order, and rewriting it like this. This bit in here is called the stem. And this bit in here is called the leaf. You ever seen one of those? Right. Olivia, you're nodding. Where have you seen that? Can you remember where you've seen that?
The 6th grade math class.
Whoa,
Yeah,
way back in the day.
very early on.
Hey, we are reliving our childhood here. Aren't bar graphs the kind of thing you see in your 6th grade math class as well, probably? Maybe even histograms. A lot of these visual things, they've not found anything better, right? They're still there. What you might get to do is a little bit more grown up is interpret some of the results that you see in it rather than just having fun creating them. Now, if you're going to do a stem and leaf, there's one very important piece that you need apart from a heading. So I'll put the heading here is a pretend one, ages of students. So we all know that that represents ages of people. And then you do, the important thing is you do a key. And you pick anything you like. So I'm going to pick 3/7. And you tell people that that means 37 years old. And you might even put a little bubble around it if you feel like it. Now, without that key, this data is quite meaningless because you do not know, well, I guess you could take an assumption here because it's ages, but suppose that was something you weren't sure what the units were. Couldn't that 41 represent 41? Right, this one here could represent 41. Couldn't it represent 4.1 or 410? That's the most likely things. If you don't have a key, you've not really done the thing. Now, in this particular one, if you take it and then you turn it side on, and then you add a few New York skyline to it, aren't you kind of looking at a histogram? You see a histogram going this way? It has lots of advantages, a stem and leaf. It's quick, it's easy to do. All the information that's written here is clearly contained in this, right? You can see it without too much thought process going on. It's pretty good data, you know, pretty good visualization. Suppose we had another set of data. I'm not going to write the raw data here. I'm going to just pretend that we know what it is. And this stem and leaf has a different name, but only slightly different name. Most textbooks call it a back-to-back stem and leaf. So can you imagine I got a lot of information about the ages of males and females in this class? And the answer came out as 15, 17, 21, 41, 47, 47, 3, 5, 6, 6, 6, and 1. Then I got the female information, and it goes 6 and 7. It goes 5. It goes 7 and 9. And it goes 1, and nothing there. This is called a back-to-back stem and leaf. The stem is in the center. Do you notice how the data gets written going this way? So when you create one, that side, the right-hand side, is kind of natural, right? 15, 17. When you go the other side, it looks a bit back to front, but you notice you put the 16 closest to the 17. So the stem in the middle is the beginning of the tree, and the little leaves branch away from it. And that's how you would create that. And then you can get questions about looking at a stem and leaf. Can you tell any patterns? Is there any distinctive shape that you're interested in? And so on. Right. Now, I am going to spend a little bit of time now talking about how to describe the shapes of various diagrams. So imagine I have let's do histograms, they're the easiest. Now, normally you do a histogram, I won't put any details in. They look like that, right? You've seen histograms before, they have an x-axis, a y-axis, there are lots of rectangles, right? What we're going to do here is we're going to imagine, for easy drawing, that I just draw a basic curve around the center of the shape, something like that. And what that will do is it will allow me to speed up the naming process. So here's our first one. Can you imagine a histogram? Or for that matter, a stem and leaf? Can you imagine it had this shape? Can you imagine that way around, right? It had this shape. What name do we give to that shape? It's got a couple of names, but which one do you think is the likely one?
Unimodal.
Oh, well done. Is that 6th grade again?
No, unfortunately, I'm an archaeologist. It's a lot of data crunching.
Okay, so this is not unusual. This is called unimodal. It means one hill. Uni, like in unicycle 1, I think it's either Greek or Latin. They're always Greek or Latin, these words. And modal, and was talking about how many modes there's one hill. This shape is called bimodal. Great. And if it's got more than 2, call it multimodal. Technically, you could keep going. Unimodal, 1 hill, bimodal, 2 hills. I guess you'd call it trimodal for 3 hills, quadmodal for 4, but nobody uses those terms. So unimodal, bimodal, multimodal. Can you imagine you create a histogram or a dot plot or a stem and leaf, and it has this structure to it? That would be one of the ways in which you would describe it. Now we're going to look at only unimodal situations for a moment. And within the unimodal world, there are 3 flavors, 3 major shapes that occur often enough that they're given names. So can you imagine a histogram that looks something like this, a histogram that had this kind of shape, or a histogram that had this kind of shape? This shape here, we say that it's symmetric. It's also sometimes called a bell-shaped curve. What about this guy? Well, this guy is unimodal for sure. Would you agree that it's got more, let's make it even more obvious, it's got more on this side than it has on that side, right? So it's kind of asymmetric, right? It's not exactly balanced. We give the name to this little piece here, we call this the tail, right? This little piece here. This is sometimes called the head. So imagine a little monster or whatever. Here's its head, here's its tail. These 2 shapes have a name. They're called skewed to the, I'll insert the missing word in a minute. And this one is called skewed to the, insert the missing word. The tail is important here. When you have a histogram that tails off to the right, we call that shape skewed to the right. On this case here, we'll call it skewed to the left. So have you noticed it's where the tail is that decides whether it's skewed right or skewed left? So suppose I had some data and I drew a histogram of it, or a stem and leaf of it, whatever it might be. And I said to you, it's unimodal. Can you see it's got 1 hill to it? If I say that it was symmetric, can you see that you get a better idea of what it looks like? If I said it was symmetric at 40, which means there, do you get even more information? If I went and said I had a class of students and it's unimodal and it was skewed to the right, wouldn't that mean I'd have a class which kind of built up to, you know, the most popular age, and then it tails off to the right? That would mean I would have quite a few older students in my class, wouldn't I? I may have a 60 and even a 70 or even an 80, right? It has data away over at the right. If it was symmetric, it might, you know, start at 15 and finish at 55. Can you see that that would be a different kind of distribution of a class? So we can use English to describe visual things. If I said that I had a histogram, it was bimodal and symmetric. Now, I don't mean this kind of symmetric, but symmetric in the more mathematical sense of it. Can you see like a double hill, like the letter M? Can you imagine what that data would look like? It would have a 2 hill thing and it would be balanced down the middle, so it would be a bit like a curved letter M. So you can describe using words this type of information. So one of the things you want to do when you try and describe a piece of a histogram or whatever it is to use unimodal, bimodal, and talk about skewedness if it has it. Here's a different thing. This is called an outlier. An outlier is a piece, is one or more than one, it can be, but typically it's one piece of data that is just exceptionally different from the rest of the family. So can you imagine I had some data that was unimodal symmetric, except I had a 99-year-old in my class. So can you imagine all our rectangles would be here, right? And then this poor little guy over here. We call that guy an outlier. It's quite a good name. I like names that at least give you a vague idea of what they're doing, right? He's on the outs, isn't he? Now, this particular guy is, I guess if you wanted to be even more specific, isn't it a large outlier, meaning it's an outlier that's a big number. But can you imagine that you had a genius 2-year-old in my class as well? Right, so that's like a 99-year-old, and this is a 2-year-old. Wouldn't this one also qualify as an outlier? It would just be a small outlier, right? An outlier that was made from a significantly different, value compared to the others. Now, you can have an outlier with any shaped histogram or data that you can have. Can you imagine you had bimodal data and an outlier? I mean, that can happen, can't it? Could you have symmetric data with an outlier? Sure. Skewed right with an outlier, skewed left with an outlier. All of those are possible. The only thing that makes you an outlier is that there's a noticeable gap of nothingness and then you appear, right? There's a space and then it's the guy on his own sum called an outlier. Now, you have to do a subjective call on this. So I'm going to have to rewrite this picture because I've written so many versions of it. Imagine that's my original picture again, right? This guy here. If you put the guy there, I think everyone here will say, yep, you're an outlier. Now, if there's a tiny little gap and then you put the guy there, would you agree that that's not an outlier? Just because there's a space isn't significant, especially towards the end. See, when the thing starts drifting at the end, don't you have nobody, a guy, nobody, two guys, nobody, a guy, it kind of drifts out a little bit like that with some spaces. That's kind of normal. So that's not an outlier. But here's the problem. Somewhere between here and here, isn't there a place where you're an outlier and then you suddenly become not being an outlier? And for every person, it might be a different place, right? If it was where this arrow was pointing, right? Pretend he's there now, right? Is that an outlier? Is that an outlier?
Isn't it dependent on, what is it? I think interquartile range.
Oh, we are going to learn that in the next section, where we actually do a calculation that takes away the guesswork. But right now we're kind of guessing, right? We're doing judgment calls. And I know these boxes look distracting, but can pretend they're not there, right? I know what to do. I just thought of a better way of doing this. Third time lucky. There's the guy. Here's my pen. My pen is pointing at an outlier, right? Is he still an outlier? Yeah, probably. Most of you are probably nodding your head, right? Still an outlier. Are we getting kind of, I'm not so sure, range yet? Some of you might say, nope, still an outlier in my book. Would you agree it's probably not an outlier anymore? and it's definitely not an outlier, right? So what I was getting at is somewhere between here and here. Isn't there a very greyish area? I'm saying roughly in here, where you're going to stop accepting that this thing is an outlier. Quite important outliers, because they tend to screw up when you do summary statistics. You know, if you do the mean of something, one really big outlier can screw the whole thing up. Give an example. If Bill Gates decided he was going to join our class, and we went and said to people, okay, let's find out how much money you've got in the bank, and after you stopped laughing, I collected the data, right? If we took everybody's data and added in Bill Gates' money, wouldn't the average be, we're all millionaires? Because he's got, like, who knows, 40 billion, right? Can you see what one Bill Gates can do to your average? It can make you think, oh, you teach a class of millionaires. No, I don't. I teach a class of normal students who don't have any money. If you were like me when you were a student, you don't have any money, right? And I got Bill Gates. So you got to be aware when there's outliers around, because they will screw up your data to no end. Now, if you're doing scientific experiments and you're collecting data, you have to be really careful about outliers and how you deal with them. You might just think, well, can't I just throw it out and say, it's experimental error, that was just a mistake, somebody wrote down the wrong number and they meant to write some other number, whatever it might be. You know, the guy who was collecting the data just screwed up. And you've got to be careful about that, because sometimes the outliers are more interesting than the run-of-the-mill data. And you might overlook some really important idea in physics, you know? Well, are we cool? Any questions? Right, so we've talked a little bit about how we're going to name these guys and how we can express descriptions of things using skewed left, skewed right, other cool things like modal and bimodal and so on. So let's see what they have here in our stem and leaf guys. Whoa, that's weird. What on earth did I do to the poor PDF? Oh good, it's figured itself out. Right, here's an example of a stem and leaf. Can you see the top there? I don't know if you need the 8 that they've gave you. 083 represents 083 or 83 points. So here is a whole load of data, and it says, what does it take to win at sports? If you're talking about basketball, the answer he listed, the winning scores at a conference championship game for 35 years. So the team that won, in this particular year, the team that won scored 98 points. So some years you need a lot more than others. So when you look at this kind of table, if you can turn your head sideways, would you agree this data is unimodal? You turn your head kind of sideways. It's got one hill, right? I would say it's got one hill. I would say it's roughly symmetric. I know it's not perfectly symmetric, but you can always stick the word roughly in, because real data is not perfect anyway. It's always got little kinks in it. Does it have any outliers? No. So if there was one game in 1910 where the team won with 22 points, I mean, it'd be up here, right? That would be an outlier. If there was other game where, you know, the team that won blew out the other team and then they got 220 points, I guess it would be down here. That would be outliers, right? But would you agree there isn't even a gap here for an outlier to live in? So there are no outliers. And I have no idea why that went wonky on me. I'm going to kill this one and move over to this fella, and we'll look at box plots, because that's not box plots, sorry, stem and leaves. Where the heck are you? There we are. We'll take a look at what your questions look like. Okay, so again, you notice there's only 7 questions. I'm going to take the solutions off here because they're definitely a distraction. I'm going to go back in and I'll do the out, go away, and then back in. Yay. So, 7 questions. Why is the answer still there? Oh, because I didn't take the key out. Darn it. Right. I'm not having a good day. I am not having a good day here. Keep screwing up. At last, we got it the way I wanted to see it. You know, if you ever watch this video, you're going to get dizzy with all the ins and outs I had to do. Right, here we go. How long did real cowboys live? You know, in the West, the Old West. One answer may be found in the book, The Last Cowboys by Connie Brooks. This delightful book presents a thoughtful sociological study of cowboys in the West, Texas and southeastern New Mexico around the year 1890. And a sample of 32 cowboys gave the following years of longevity. So I guess you could collect that data and maybe be going round old graveyards and looking at the ages that they died, you know, something like that. Maybe they've got written records, but here they are. So can you see that the cowboys range from, well, the first thing, if you're going to do one of these stem and lease, this first column here, well, let me make an assumption. Are you seeing this first? Okay, good. So this first column here is going to be the stem, right? And then this one to the right is going to be where the leaves go. So when you scan through this set of data, what was the youngest age in which someone died?
47.
Okay, let's see if I can even find that. I'm sure you're right, my scanning's not great. Oh, there it is. So can you see that this is going to start with a 4? Represents all the 40s, then a 5, then a 6, and I guess I should keep on going. 7, 8, and 9. And that is amazing to me. I don't know if it's amazing to you. But way back in 1890, I think 1890 has not a lot of medical help, right? A lot of diseases that just kill you, right? You get a bad cut, septicemia, poison, boom, you're out of it. It's amazing that you got someone who lived till they were 90 and another person who lived till they were 93. I mean, that's kind of interesting to me. Right, so now that you've got this set up, the next part is how do you fill these in? Well, let me jump around a little bit. Let's do the 90s. There's a 90, right? So you do a 0 in there. I'll put a comma in. That's probably the best way to separate them. And there's 1 to 91s. And I see a 90, where is it? I lost it. I see a 93 and a 97. Is there anything else?
92.
There's a 92? Okay. I can only see 193 and 97. Can you see any more than that? Right, so I'll assume that I got these guys correct. So you see what I'm doing there is I'm putting the data in, but you notice that I have to also remember to put it in the order. Right, 91 gets written down, the 1s get written down before the 2 for the 92, and you finish with the 97. You see that? That's part of what this should look like. Now, up in the 40s, what kind of 40 did we have? Because it was in there, 47. Is there anything else in the 40s, or is that the end of that one? I can't see one, but that doesn't mean it's not there.
Yeah, I don't see one either.
Okay, so we'll call it good, right? So can you imagine, I'm not doing it, but can you imagine going through the 50s, through the 60s, through the 70s, and through the 80s? So basically, you're constructing, with a little bit of framework help, what a stem and leaf would look like. Wow, you got to do something with your voice, young lady. I'm sure you're asking or telling me something, but unfortunately it didn't come through too well. I've kind of confused myself here. Where are we? What is? Right, I'm going to have to stop this and go back in because I can't find it. I'll just mute everybody. So if you have to say something, you can hit the space bar, and that probably will save me a lot of grief. So there we are. Right, can you imagine finishing this guy off? So it then goes on to part B then. Considering the following quote from Baron von Richthofen. Is that the same guy from the First World War fighter pilot? You remember Baron Richthofen? In the cattle raising on the plains of North America, cowboys are to be found among the sons of the best families. The truth is probably that most were not drunkards, gambler a lot, or quick on the draw, fire with their pistols. Does this data distribution of longevity lend credence to this quote? But I know we don't have the middle one, but I'm just looking at the 90s. Would you agree that this data looks like cowboys pretty much did live a long time? Right? 47 is the youngest death, and there's a lot of 90s. I'm pretty sure what you're going to see is, 3 or 4 in this range, 5 or 6 in this range, whatever. Some kind of pattern like that. So yes, these cowboys certainly live longer. And they even go in and tell you, hello, yes, call it good. So that's the type of question that you're going to get in the homework about stem and leaf. Do you see it's create a stem and leaf and then maybe answer a little question or two about it? I can imagine a situation where they may have an outlier and they ask you about, is there an outlier here? Now, for this to have an outlier, I know the data doesn't work, so let me pretend I've got a blank one. Can you imagine we've got numbers here, 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 and then nothing, 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 and then one guy. You see, that would be what an outlier might look like, with a big gap of nothingness before you hit the fella. Here's some data. Figure out what your stem's going to be. Here's an issue. Do you see how the smallest number is 9? In fact, I think that's the only singular guy. You put 9. Then you do 10s. And then you could do 20s and so on. Here's a question. What should I put on the top left-hand box?
Would you put 0?
I would.
Yeah.
Rather than blank. Because blank is a kind of, did you miss some out? No. 0 makes more sense, because wouldn't 0 stroke 9 mean 9, whatever this is measuring?
Yeah.
Right. I don't know what the answer to this is, because you're going to have to wait until you finished it. Here is a whole load of stuff, and you're going to make a stem and leaf display for the average daily length of stay in days. So you don't need to worry about Alabama. You only need to look at this last column of data, at least for this one. Right? See the last column? So I guess the first thing I'm going to do is I need to know what number goes here, because I need to know where to start. If you scan through this data, it's all decimals. What's the smallest number? I can see a 5.5, but if you see some smaller, tell me. I can see a 5.2 now. Anybody beat 5.2? Okay. If that is guaranteed to be the smallest one, wouldn't this be 5 point somethings, 6 point something? Oops. 5 point something, 6 point something, 7 point something, 8, 9, 10, and 11. Right? And for instance, if you wanted to tell somebody 5.3, don't you do it that way? Wouldn't the key say 5 vertical stroke 3 means 5.3 days? Right, so we all know what that means, because right now it could mean 53 days in hospital, which I don't think would be a realistic number, right? Now, you're going to fill this data in, and do you see skewed left, skewed right, bimodal, right? I don't know what that data is going to be. It's hard to tell, but once you've finished it, hopefully this question will make more sense, won't it? So when you're looking at data and you want to tell if it's skewed, you have to pick the data up and you have to turn it this way or turn your head on the side, right, from left to right, so you can see which way it's skewed. It might skew left, it might skew right. Here's a early period, recent period, make stem and leaves. Here's golf tournaments, make some stem and leaves. Here's some data on something to do with nicotine. And here's a back-to-back. Actually, I think their key is a little bit confusing, but C5 red line to red line 0 means 25 centimeters at the site, and the other one means 20 centimeters at site 2. So here is site 1 data and this is site 2 data. When I look at this set of data, let me ask my own questions then. If you're looking at site 1, which is this data here, right? Don't you have to turn your head kind of that way to see it, right? You want to see big to small. Actually, I should do it the other one. When I look at this data, would you agree it's probably unimodal? I know there's a little kink there, but it's mostly unimodal. Would you say it's roughly symmetrical as well? Yeah, don't worry about a couple of digits here or there. There's always going to be some bits out. That's why you can say roughly at the front of everything if it makes you feel better. And this data here is, I'm not even sure how I would describe this data. It's almost like 2 different sets of data, isn't it? There's a huge gap in the middle. So these numbers are coming from one place and these numbers are coming from some other place. Weird. And that's the end of that fella. So we have got one more guy that I want to get done today, which is the one that I've been skipping. 3-1. Time to do it. Frequency tables and histograms. Right. Now, unfortunately, and I don't have any control over this, as I said to people earlier, this section is as clear as mud. They just made it so much more awkward than it truly is. So what I'm going to be showing you is what I wanted you to get from this section, even although if you read the textbook, you might not get that from it. So let's look at first situations. Actually, let's collect data from ULUP. That's a good idea. So I'm going to close off this for a minute. Right, I've got you all here. Let's collect data on number of siblings. Now you won't be able to see it until I return back here, but I need you all to be here. So I'm going to do number of siblings. And the second column is going to be frequency. So this is going to be my first frequency table. Right, so here's the rules. We're going to count your brothers and sisters. So you obviously count, so the answer is guaranteed 1. You count your brothers and sisters, and you count your half brothers and your half sisters, but you don't count step brothers or step sisters, right? So I've made that as an arbitrary rule, just so we're all measuring the same kind of data, right? So if you look at the bottom, do you know you've got that little reaction icon that you can stick a thumbs up on? So you will stick a thumbs up on as we go through this. How many, if any of you, are an only child? I don't see any. Okay. How
Well, there was
many?
one.
Oh, there is. Where is it? Oh, I take it back. I missed it. You're right. I put it in now. You're counted. How many are two? If you want to share, you do. If you don't want to share, don't stick your hand up. Okay, there are two of you. That's interesting. Right. How many are three of you? Oops. Wait a minute. There's three in that. That was too slow. Right. How many threes? 1, 3 in the family. Right. You're keeping that up. 1, 2, 3, 4, 5. It almost got it before it disappeared. Anybody with 4 in the family? Oh, well done, Kerry. Anybody else? Michelle? Michaela, I should say. Isaiah? Wow. Oops. 3 of you. 5? Okay. 6? 7?
I have
8?
7.
Way, good. Well done. 8? 9 or 10? Right, I'm in. I'm 10. I'm one of 10 children. I'm number 8 in the family line. Chloe, you're going to have to close your mouth. You'll swallow things if you're not careful. Well, in
There's a
fact,
lot of children.
that is a lot. My dad was a coal miner, and he liked lots of kids. My mum was a natural mother. I mean, if you
I
were going
cannot
to
imagine.
if you were going to create a mother, my mum would be it. My mum was about 5'2", tiny woman.
Aw.
And you know when babies cry, my mum could pick up anybody's baby that was crying, and within 5 minutes it would just settle down. She was
Wow.
just so good at it. Me, I just need to look at the little things and they ball out crying.
And
So
they cry.
I didn't inherit that from my mum. So that was it. So oh, it's in my brain. I got to get it out because I'm easily distracted. I told you I was number 8, but the way this worked out, well, didn't work out. God or nature did it. Their first child was a boy, which was my older brother Billy, and then they had 6 girls, and then they had me. So
Sorry.
yeah, exactly. When I was growing up, I had 7 mothers. I had my mum and my 6 big sisters. And they used to make my life an absolute misery. I couldn't get away with anything, right? You know, when you're a little 4 or 5-year-old, you wanted to do something you weren't meant to do, like cross the road to go someplace that you're not meant to cross the road to. Hadn't a chance.
Wow.
Yeah. I still like girls, go figure. So, and I do like my sisters now. They're much, much better when they grow up. They weren't so nice to me when they were younger. Right, so I'm now going to switch back to show your data. It's a bit of a mess, I apologise for that, but at least you'll get the gist of what I was talking about. Essentially, you just create a table, maybe I should do it again, where you do number of siblings, and then the second column is always frequency. So you had 1, you had 2, you had 3, you had 4, 5, 6, 7, 8, and 9, and then finally me. And so the pattern went 1, 3, 5, 3, 0, 0. Something's not right here. Oh, 7, we're good. 8, 9, and then 1, right? So that would be an example of what's called the frequency table. It gets its name because of frequency here, right? Now, what you want to probably do with a frequency table is convert it into some visual form that's easy to see. And the most common thing that we do with a frequency table is to create what's called a histogram, which I'm sure you've probably seen somewhere. It's one of the most ubiquitous types of diagrams that you get almost everywhere, right? From, you know, if you look up an economics textbook, there are probably histograms everywhere, right? It's the kind of thing you'll see a lot of. So let's do a very miniature version of it. Along the horizontal axis, you put a label telling people what you're counting, in this case, number of siblings. And the vertical axis is going to be the frequency. And here you might say number of siblings as well. That would be the heading, which is kind of duplication of that. And then you go 1, and you go, what's the biggest number I need? 5. So 1, 2, 3, 4, 5. So 1 got you 1, and 2 got you 3, and 3 got you 5, and 4 got you 3, and 5 got you nothing, so you don't do anything there. Then you have 6, and of course no planning by me. 7, you got 1. Okay, I kind of screwed up here. Can you pretend there was more paper? Ah, I got an idea. Improvise. 8, nothing there. 9, nothing there, and right at the end, 10. So do you see the features that a histogram has? The horizontal axis is whatever you were counting, number of siblings in this case. The vertical axis represents how many people fall into that category, right? There was 5 people with 3 children and 3 siblings together. And you just basically build a couple of features. Do you notice that there is no gaps? When you do a bar chart, it's red, a little space, green, a little space, blue. Or if it was high school space, all the ways, always a space in a bar chart, never a space in a histogram, which is what this cell is. Now, I don't have an awful lot of data here, so I'm kind of bending the rules a little bit. Would you say that this data is unimodal? Yeah, it's got one hill. It's not a big hill, but it's a hill, right? This one is really pushing it. But if I took this data and I draw this kind of thing, it's kind of skewed to the right, isn't it? Maybe a little bit. I wouldn't bet my, my last dollar on it, but it is kind of skewed to the right. Do you think I'm an outlier? Do you think 10 would be considered an outlier in this data set? That one there. Yeah, I think most people would probably consider that an outlier. What about 7? Right, some of you are nodding, but I don't think everyone is nodding. Is 7? Yeah, but if I moved it to 6, you'd probably say no, right? If there was a 1 on 6, you wouldn't think of that as an outlier, right? That's probably the grey area where the outliers start, right? And you can have more than one outlier, right? You can have 2 or 3 outliers if it works out that way. Are we good with that? Right, now, what is left? Well, all we need to do now is look at what's called a grouped frequency table, and that will be the frequency tables done. And then I'm going to have to look at or go over the homework questions, which are a real pain in the butt, as I kind of mentioned at the start. And I'll probably be putting up a PDF with some help on those questions, because I don't like the questions. I guess that's what I'm trying to say. Okay, let's look at grouped frequency. Now I'm going to use you lot for the data again, if you don't mind. We're going to do the kind of the vote thing. Now, I'll tell you why we need group frequency. You might think I'm going to say, what is your age? Which I am. But I don't want to know that you're 24 or 26 or 33 or whatever your age may be. Because if I just collected that data, can you see that I'd have a pile of numbers where there would be, if I tried to do a normal frequency, wouldn't it go something like this? 17, one person, nobody 18, nobody 19, nobody 20, 2 people 21, nobody 23, 4, 5, 6, 7, a 28-year-old and so on. Wouldn't the table be this big? with mostly zeros and a couple of ones and twos in it. The whole idea of having a frequency table, any kind of frequency table, is that you take the data and you try and put it in a format that allows you to see things. So what we're going to do is we're going to group the data. So that means I'm going to have your age, and you only take part if you want to. You don't want to do your age, don't worry about it. We won't use you. Although you are allowed to lie. So you can do what my sister did, one of my older sisters, as you know, I've got plenty of them, but one of them in particular, when she reached 31, she decided that was it. And every birthday after that, she was a 31st birthday. Right? And she was 31. And it was a kind of joke in the family because we all kind of joined in with that. We bought her, you know, birthday cards with happy 31st, and the birthday cake had 31 candles, you know, the whole thing. We all went with it. It was great. And then her oldest son turned 31. And so there did come a point in time where she had to let go. So she just has birthdays now without numbers. Okay, so I got that family story out with. The first group I'm going to do, oh darn it, I really have to visually show you this. If I say it, you probably won't get it. It's not that it's hard, it's visual. Right, I am going to do 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, and 60 to 70. Now, when you look at these groups, anybody who's in the age 10 to 20 all get clumped together as one group, and I'll count you up and you'll go here, right? The 20 to 30s all count and they go in here. You might notice that this group finishes with a 20 and this group starts with a 20. That is very common when you group data, that you share the last number with the beginning of the next group. So I guess the question you should then say to yourself is, well, if someone is 20 years old, which of the two groups do they belong to? They can't belong to both, that's double counting, right? They must belong to one. So this is how you read that. I'll use it on the last group. This is for 60-year-olds up to, but not counting, 70-year-olds. So this group would be 10-year-olds up to, but not including 20-year-olds. So see if you're 19 years and 364 days and your birthday's tomorrow, you go here, right? If you turn 20 today, you now belong in this group. 20-year-olds up to, but not including 30-year-olds, right? Do you see how it's going to work? Right. So first, I have to go back to your screen so we can count all the hands up. How many of you are in the 10 to 20-year-old? And remember, you don't count yourself if you're 20, right? You belong in the next group. How many are 10 to 20-year-olds? 1, 2, 3, 1, 2, 3, 4. 5 of you. Okay. How many are in the 20 to 30-year-olds? 4 of you. How many? Yeah. How many on the 30 to 40-year-olds? If any? Any? Stacey, you are not that age. 30 to, well, you might be, I guess. I don't know what your age is, so you forget that. 30 to 40-year-olds, vote again. Okay, we got one person. 40 to 50s. 2? 2? Okay, let's just keep going. 40 to 50s. 1. 50 to 60s. Nope. And me. Right. So can you see what the group frequency table now looks like? No, you can't. Can you now see what the group frequency table looks like? So how does that transfer over to a graph, right? Well, when you draw it, you're going to get what's called a grouped frequency histogram. So you can have a frequency histogram or just histogram, or you can have a group frequency histogram. Now, along the bottom,
I have a quick question.
yes,
I know that in the reading it was saying that when you said 10 to 20, 20 to 30, but then sometimes it goes 10 to 19 and then 20 to 30.
yes.
Why would you do the difference?
I dislike this chapter in the book with a vengeance. They do it in a very unorthodox way, and I don't want to teach you that way, because that's not the way you would really do it in the outside world. Now, that does mean that there's going to be quite a few questions in that section that's just going to drive you crazy. That's why I'll be putting solutions up to show you what they mean when they put data in, right? And we'll just let that slide. And for that same reason, I'm probably going to avoid any kind of questions in exams from that section, because it's just, I don't want to encourage bad behavior. This is how group frequency tables should be and are in the vast majority of situations going to be. If you go and do a search online and say group frequency table, I'm pretty sure this is what you're going to see and not their version. So I'm going to start at 10. I'm going to make a mark at 20. I'm making a mark at 30, one at 40, one at 50, and one at 60, and finally one at 70. And that's going to be age. And it looks like I don't need any kind of big scale here, because it looks like 5 is the biggest number that I need to accommodate. And then 10 to 20 is 5. 20 to 30 is 4. 30 to 40 is 2. 40 to 50 is 1. Then there's nothing, 50 to 60. And then there's another 1. And that just happens to be the data that we have got here. It's pretty obvious that this class, would you agree, it's heavily weighted to the younger people? I mean, that's the majority of people are in the young age group, and the old folk get me at the end, which is not a surprise. Are we cool with that? Right, so these are the ways they should have in 3.1 done histograms, done frequency, done group frequency. Of course, the person who wrote that textbook decided to go their own unique way. So for the time that we have left, because I kind of want to cover chapter 3 today, and then we can cover chapter 2 today, and we can cover chapter 3 on Thursday, right? I think that's a natural starting point as well. So if you can hold off for a few minutes while I do that out and in and can you see me thing. Let's view it. Right. That's the wrong section, sorry. Let's try it again. Okay. Now, you can't see it yet, but it is coming up shortly. Going to do it. I just thought of a good cheat that's going to save you and me a fair amount of work. I have put the answers up so that we can see them. It won't cover all the questions, but at least you'll be able to see them. So when you go back and look at this video, you'll be able to see what answers belong in each of the boxes, right? That saves me actually having to write down what the solutions would be, right? So, hey, why can't I see? Oh, darn it. I forgot to put the key in. My apologies. I'll be back in a second. Right, we're good to go. Okay, so the first one says stats in practice. There's a little 1 hour 45-minute video, and it goes on and it says this video indicates that most of all the heroin in the United States comes from 2 countries, and they tell you what the answer is. Actually, you could probably watch the video, and these questions are not going to be that difficult. Right, here is the first thing that I haven't even spoken about. They've got a thing called the class limit and another thing called the class boundary. If you go and look at the textbook, they'll give you a little definition of each. But class boundaries are not possible data values. Right, if you collect data that is a whole number, 5 children in the family, 6 children in the family, 7 children in the family, right? If you take 5 children in the family, you're going to be looking at 4.5 to 5.5, because any number in that range would be rounded off to 5. You see why I don't like this question? If I was doing a histogram, I think it makes perfect sense to have a 5 in the bottom and have a rectangle for 5 kids. Not to have a rectangle that has 4.5 on one side and 5.5 on the other side, and that represents any number that would round off to 5. Do you see how weird that would be as a way of representing 5? But that's what it is. So I'll pause this, or you can pause your video and you can see who the right guys are, and you can maybe look through them. Class limits, on the other hand, are possible data values. So class limits would be 5, 6, and 7. Class boundaries would be 5.5 and 7.5, right? Things that can't exist in the data set that you're looking at. Question 3. A data set has values ranging from as low as 20 to as high as 52. And it says, what's wrong in using these limits here? And if you look at the intervals, which are that annoying thing where they finish at 39 and finish at 40, would never do that. But that's not the problem. The problem's even simpler than that. Do you notice that the biggest number is 52, but the last interval finishes at 48 to 49? That's the one that you pick. So even the answer wasn't the obvious one. Now, in this case here, it's very similar, question 4. We're coming up on question 5 now. A data set has values ranging, oh wait a minute, I'm getting deja vu here. Oh, a data set has values ranging from 10 to 50. The class width is to be 10. So you imagine there's 10 numbers going from side to side, essentially. What's wrong with using these particular groups for a frequency table with a class width of 10? Well, the classes listed have a width of 11. And you think, no, they don't. 10 to 20, 21 to 31, 32 to 42. Well, let's check it out. If you count on your fingers all the numbers from 10 to 20, here we go, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Aren't there 11 numbers? Right? 10 up to 20. If you count 10, 11, 12, 13, all the way up to 19, 20, there's 11 numbers there. So that's what's wrong with that. The class width, if you like, is how many numbers are in my group. There is 11 distinct whole numbers in that group. And not like this section at all. Now, this one is not so bad. You're a manager of a specialty coffee shop. Oh. Do you know how I say specialty? How do you say that word?
Specialty.
Yeah, my wife says I pronounce too many syllables. It's a habit of how we speak. That's how you would say it in Scotland. That's how you say it in Britain. Anyway, the manager of a specialty coffee shop, and they collect data throughout the day regarding waiting time for customers from the day they enter the shop until they pick up their order. What type of distribution do you think would be the most desirable for the waiting times? Skewed right, skewed left, or symmetric? Right, so if you collected you know, how long did you wait? 10 minutes. How long did you wait? 2 minutes. How long did you wait? 29 minutes, right? If you collected that data and you were wanting to treat your customers the best way you could, the skewed right distribution should be the most desirable, because that would mean there's a lot of short waiting times and only a few long waiting times. Do you know, I would argue against that. If you go into a coffee shop for the first time and it takes you 45 minutes to get your coffee, even although you happen to be the unlucky guy that had to wait 45 minutes, I'm probably never going back to that coffee shop. Me personally, I think that that shape should be symmetric. Right, sometimes you get really lucky, but most of the time you're going to wait 10 minutes and that's kind of it, right? 10 minutes, most people are done. Occasionally you might have to be 15. Do you see? That would be a much more preferable, for me anyway, that would be a much more preferable one. So what is awkward is that sometimes questions can be very subjective. And so there may not be a right answer. There may be, for me, this is the right answer.
The problem I had with this section specifically is, a lot of these questions are so subjective, and you kind of have to get good at guessing
what they think the right answer is. Yeah. So when you go into, hopefully, have you used up all your 3 guesses yet? Did you fight your way through it, Olivia? Is it over with?
Oh, no, I managed to figure it out.
Okay, getting 3 shots helps, but you know, even then you can sometimes miss, right? Now they go on, they talk about distribution times, and I think we're looking at some histograms here. I'm just going to scan through these slowly so that when you go and do your homework, you can find out which one it is and just click on it. Just looking at this group here, can you see that the interval spacing is really weird? I don't think 8.5 to 12.5 is a very sensible interval, not in my book. Would you agree? It's a kind of clunky interval. I mean, 8 to 10, 10 to 12, 12 to 14, that would make sense to me, right? 10 to 20, 20 to 30, that would make sense to me. But this 20.5 to 24.5, not really convinced that that's a good answer. But anyway, here are all the class boundaries. So if you're looking at what the class boundaries are, that's the numbers you're going to do and the frequencies. Although I've got a feeling that this answer is not correct for this picture. So you might want to check that out. Here is a weird one, but nonetheless, I guess it works. If you took this set of data and you made a histogram using these boundary points, right? These numbers to start and finish, 53.5 to 99.5, weird interval, but imagine you did that. You see it in the picture? Do you notice why this is the right picture? Isn't almost every single piece of data in the range somewhere between 53.5 and 99.5? And then that poor little guy there, that's your 1 to 8. So that's your answer. That's the picture. And then it says, look at the last one. Does it appear to be an outlier? Right. Would you agree this poor little guy's an outlier? Look at all that nothingness. I mean, just look at the data, right? It finishes at 98 and then you don't see nothing until 280. I mean, that would be an outlier just looking at the data. So that's why that's a yes. And then they go, and they give you choices and that's going to be the right answer. That one there, I'm zooming by totally. Now we're getting to a guy that I can actually get some, I like this particular kind of thing. And I just realized, thankfully we've still got 12 or so minutes, that I forgot to tell you about it. So I'll write the heading down, then we'll return to it, and this will get you through the last few questions. This is a cumulative frequency diagram. I'll leave that one there. Your answer is going to be this one here when you get to it. There's that one there, that one there, that one there, that one there, right? There are a whole bunch of them. You know, you can always pause this if I zoom too quick. And here is your data and a whole load of numbers. I'm pausing on that one just for a few seconds. And then we'll finish with a couple of these guys. And then, okay. So let's show you the bits and pieces. So hopefully you can pause at any of those questions I zoomed really quickly by. Let's show you cumulative frequency, and over here I'll do dot plots. Imagine that you've already collected data, and we'll have here age, and we'll have here frequency. And we'll have a third column, which is called the cumulative frequency. Right. Let's suppose that you went to some kind of children's club and you were looking at the ages of the various children. So there was 5-year-olds, 6-year-olds, 7, 8, 9, and 10-year-olds went to this club. And the data that you got was there were 3 of these kids, there were 4 of them, there were 7 of them, there was 2 of them, there was 3 of them, and 1 of them, right? That's a frequency table, right? Just a normal one. Can you imagine drawing a frequency graph for it? Wouldn't be too difficult. So who's the cumulative guy? Well, you do the data a little bit differently. The first one is still 3. This number isn't 3. It's those 2 added. It's the cumulative effect. It's now 7. Right. The next one, cumulative, 14. So what you're saying here is that there are 14 kids 7 or younger. Right, that's what that 14 is representing. That 7 is representing there are 7 kids 6 years or younger. Right, would you agree the next one goes 16? The next one goes 19, and the last one goes 20. So a cumulative frequency table is not that difficult to create. Would you agree? You just add the previous answers together. Now, what does that fella look like? Well, along here, you can put age, and we'll go 5, 6, 7, 8, 9, and 10. But you don't do a histogram with these. Have you ever heard of a thing called a line chart? It's basically a chart made up of lots of lines zigzagging along, line chart. It's going to look a bit like that. So the biggest number I need is 20. So I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And
just a little bit.
A little bit louder, please.
Can you move your paper up just a little bit, please?
Oh, wait. You see it?
Just a little bit.
A little bit more?
You're good. You're
You're
good.
good. Okay, so what I'm going to do now is 5-year-old cumulative frequency is 3, which is about here. 6 years old, the cumulative frequency is 7, so it's about here. 7, it climbs up to 14, which is about here. 8, it climbs up to 16, which is much more. 9, it climbs up to 19, a little bit higher. And then 10, it climbs like that. And then you just basically go like this. And that's what a cumulative frequency diagram looks like. Does that make sense? Now, all cumulative frequency diagrams have to go uphill. Because isn't the next answer, the worst it can be is the same number as the previous one? Right, you just add 0. But most of the time, won't you add 1? And it can sometimes go up in different shapes. So, can you imagine that I had one that went up like that? Wouldn't that be very linear? Wouldn't that be like if everybody had 3 in their group? You'd add 3, add 3, add 3. It would be a straight line. It would be linear. And you could get ones that do this kind of shape. Wouldn't that be representing a lot of people at the beginning and not too many towards the end? It's going up fast at the beginning and going up quite shallow at the end. So you can imagine different sets of data might generate different versions of this particular curve. I believe it's called the Nojai curve. At least that's the name I call it. I'm pretty sure they'll probably call it that. And 6 minutes, we're going to do dot plots. Dot plots are easy. Even this book can't screw them up. Can you imagine that we collected data on the ages of people who maybe go to a church, right? So they went on one Sunday and they just asked everybody what their age is. So these numbers represent age. And what you do is you do a little circle. Sometimes it's a little dot, but a little circle is more common. And what you do with this dot is you put it in. So you might have had a 10-year-old, 3 11-year-olds, a 20-year-old, a couple of 30s, maybe more of them, a couple of them, and so on. Maybe a little outlier up there. I'm not being particularly neat here, but can you imagine what each circle represents? It represents one person and their age. So that would represent there's 2 people in this church who are 70-year-olds. There's 1 person who's 90. There's 3 at 30. And my scale's horrible, but can you imagine those 4 next to it represented 32-year-olds? So this here is a dot plot. And if you take a dot plot and you kind of do a rough shape through it, you can answer the same kind of questions like, is it unimodal? Is it symmetric? Is it skewed left? Is it skewed right? Unfortunately, the way my data looks right now, it doesn't have a shape, so I'm going to add some data points to kind of make it work. Okay, now I've got some data points, I can ask a question. Looking at this shape, what do you think it is? Unimodal or bimodal?
Uni model?
Yeah, I think this is definitely a hill. I'm not convinced that this is a hill. This is more like a little bump at the end. A predominant hill, so I'm going to have to change my data set again, would be if this happened. You see, it's probably bimodal now.
Yeah.
Little bumps don't count because you're always going to get a randomness in data. There's always, especially towards the ends, there's little bumps that just kind of look more important than they truly are. In this data, it's now bimodal. Do we have an outlier?
90.
I would agree with 90, right? And back to what your thing is, Olivia. Are they kind of subjective about who's an outlier when you look at some of these questions? Or did they give any outlier type questions even? Can you remember?
I don't recall there being any.
Right, so they didn't even bother to ask you what would have been a really good question about outliers. The good news is that outliers happen later on, because Michaela was talking about it. You can actually do a calculation which tells you when a number is extreme enough to be considered an outlier. And so you don't need to do this, I think it's one, somebody else says, nah, I don't think it is. Right, they're a kind of balance. We do away with that, and it's kind of cool. There's a version, there's a test when you use quartiles. It's called the upper and lower fence test. And there's another test that you use when you use standard deviation, basically. If you're more than 2.5 standard deviations away from the mean, you're considered an outlier. So that'll come in a different section, right? Actually, I believe that's going to come in chapter 3. So I think this is I think this has been better on your brain. It's certainly been better on my brain. I think we've at least had, it's enough for you to reasonably absorb, right? So you're going to come and Zoom me or shoot me emails when things don't work and you're not sure about it. I'll try and get that 3.1 part of this, well, this whole video, but the 3.1 part online as soon as I can, so that you may want to skip that homework until, unless you've done it, right? Until then, and then you can go in and do it. And that's about me. Any questions before we call it a day?
Nope, I think I'm okay.
I guess I could ask you, are you comfortable with the 2-hour thing? You're
I'm
okay
all
with
about
that,
the
right?
2-hour thing. That is just fine.
Okay,
I
so
think everybody likes that.
everybody is happy, so I'm not inflicting my opinion on you. It's everyone's opinion. It's a good idea, or at least everyone that's telling me it's a good idea is agreeing. Okay, well, have a nice couple of days, and I'll see you on Thursday. Try and get started on 3 because there's a lot more work in 3 than there is in 2. The one I didn't go over is the review, but I think the review's got like 7 questions in it as well. Chapter 2 doesn't have an awful lot of questions in any of the sections, I think. Maybe 3.1's the worst. Okay, bye-bye. See you guys on Thursday.
Thank you. Bye.
Okay, anybody here want to ask me a question? You're still here? No? Brianna, you ready to ask me a question? Or are you just taking your time? Okay, I'm assuming you just have gone for a coffee. Bye-bye.